Now we'll consider the syntax and their operation or the function. So under indirect addressing modes with a single data memory operand, and we look into a circular addressing. So operand syntax is this ARX. So X is nothing but the value from 0 to 7. So it is any auxiliary register which is AR0, AR1, AR2 till AR7. So operand syntax, if it is ARX, then the address is nothing but the value which is in ARX. So that is a function what it is going to happen if I use this in the instruction. Similarly, if the operand syntax is ARX minus, then the content of ARX is nothing but the address, and the content of ARX is decremented by 1. So that is the sign what we look into this syntax, which is minus. Similarly, if it is ARX plus, then the address is stored or transferred into the auxiliary register AR, and the content of AR is incremented, and the incremented content is stored in AR, or the incremented content is pointed by AR register. Similarly, plus ARX. So here initially the address or the content of the AR register is going to be incremented, and it is the address, or it is stored as the address, and again the content of AR register is incremented by 1, which was the previous address. So if the plus sign is before the auxiliary register syntax, then the increment operation is to be done first, followed by the transfer. But whenever I go with the plus after AR register, then the transfer is done first, then increment. So similarly, ARX minus 0B. So that is the content of AR is nothing but the address, and the content of AR is subtracted from the content of AR0. So this is normally AR1 or AR2 or AR3, etc. And the content of AR0 is subtracted from the content of ARX. So any auxiliary register content is used, and the content which is stored in auxiliary register 0 is subtracted from the content of auxiliary register which is pointed by the instruction. Similarly, ARX minus 0. So now we just see that B represents the bit reversal. B represents the bit reversal. Now ARX minus 0, it is just the subtraction of the content from AR with the content of ARX register. So here we don't see the bit reversal operation done. Similarly, ARX plus 0, so the value of ARX is nothing but the address, and the content of AR0 is added with the content of the auxiliary register ARX. So similarly with the ARX plus 0B, similar to this instruction, which is the bit reversal addressing mode. Next is ARX minus percentage. So percentage is one which specifies the circular addressing. All the operations are same, but it is the decrement operation done with the circular addressing operation. Similarly, if I consider minus 0%, it is pointing to the register 0 or auxiliary register 0. Then ARX plus percentage, it is same as the circular addressing mode used with the increment operation. Then, so these instructions are normally used for convolution and correlation, which is used in FIR filter. So the circular buffer, what we normally consider, is a sliding window which contains the most recent data. So that is what we are using in terms of CIRC in the function of an instruction which is defined in the syntax earlier. Then circular buffer size is taken as capital R and must have a boundary which is n bit, where 2n is greater than r. So if I consider it is 8-bit boundary, then it is 16, which is greater than the buffer size. So the boundary will be greater than the buffer size. The circular buffer size is named as BK or buffer size BK specifies the size of the circular buffer. So the circular buffer will have a size specified and it is taken as BK. Then effective base address EFB is obtained by zeroing the NLSBs of a user selected ARX. So effective address is calculated or identified by just providing zeros the LSB bits of a user selected auxiliary register. Then end of the buffer address. So we are going to consider start of the buffer address and normally the end of the buffer address. So they are obtained by replacing the NLSBs of ARX with NLSBs of the buffer register. So this is what we do if we consider the instruction which is used for circular buffer. So we look into that in detail later. So this is the syntax. If 0 index plus step is less than bk, then index is index plus step. Index is nothing but any address which what we consider in any instruction. Else if index plus step, if it is greater than or equal to bk, then index is equal to index plus step minus bk. So if I just consider the buffer size as bk say 100 and if I consider the step is 50, then 50 should be greater than or equal to 100, so that is not possible in the second case. So if it is first case, 50 is obviously less than the buffer size, then index is index plus step. So index, if I consider it is 50, 50 plus say step size is 50, so index will be equal to 100 and the buffer size is equal to 100. If not, then these else if conditions are going to be executed or it is going to be used. So this is the structure or block diagram of a circular addressing mode of TMS320 processor. Then circular addressing mode implementation of TMS320. So here we can see effective base which is having the higher order bits and ARX which is also consisting of higher order bits followed by the number of bits 0 to n-1 bits. Similarly, it is higher LSBs or what we call it as higher order bytes and these are lower order bytes. Then comes a bit reverse addressing. Bit reverse addressing is normally used for FFT algorithms and AR0 will specify one half of the size of the FFT. So this we will see when we consider the bit reverse addressing in detail, where we are going to identify what is the present index depending on the previous index value specified in the instruction. So the value of AR0 is 2n minus 1 and n is equal to FFT size which is equal to 2n. So we'll take what is n and by considering n is equal to 4, 8 or 16 we can identify the FFT size. Similarly, AR0 plus AR which is a selected register, AR is a selected register, that is equal to bit reverse addressing. So the carry propagation is from left to right instead of right to left. We are going to carry say for example 1 and 1 is added with 1 and 0. So normally we perform addition, 1 plus 0 is 1, 1 plus 1 is 0 with carry 1. But here we are going to do it in a reverse way because it is a bit reversal addressing. So 1 plus 1 is going to be 0 and this 1 is carried here. So this is 1 plus 0 which is equal to 0 with the carry 1. So this is the bit reversal what we are going to consider. Then dual operand addressing. So dual operand or dual memory addressing is used for the instruction that will perform two operations simultaneously. One is a 32-bit read or a single read which is 16-bit read and a parallel store. So reading and storing. So it is performing two different operations simultaneously. And these instructions will access the operands using indirect addressing. So there is no direct fetching of data and executing it, but it is going to be performed indirect way. If in an instruction with a parallel store, the source operand, the destination operand point to the same location, the source is read before writing to the destination. So that is what we consider. So data memory operand is going to be used and they are going to be one read operation and one store operation, or and this two it may also have two reads of 32-bit or one read, single read, which is 16-bit. So only 2 bits are available in instruction code for selecting each auxiliary register in this particular mode. So just for the auxiliary register AR2 to AR5, we can use this dual operand addressing. Then ARUs together with these registers provide capability of accessing two operands in a single cycle. Normally when we go with a single cycle, only one operands are going to be accessed, but if I use this uh, in a single cycle, we are going to access two different operands, which is done by using this ARAU register, because we have two ARAU registers, ARAU0 and ARAU1. And this is the syntax of how the address is generated using dual data memory operand addressing. So this is what we consider 0 to 16. 0 to 15, a total of 16 bits. Then function of different field in dual data memory operand addressing. One is opcode. This field contains the operation code for the instruction. So this is the function of an opcode. Xmod, it is defined the type of indirect addressing used for accessing the X memory operand. And XAR, X memory auxiliary register selection field, defines the auxiliary register that contains the address of X memory. So either we stick on to X memory or we stick on to Y memory in the set of instruction what we use. Then Y mode, it defines the type of indirect addressing mode used for accessing the Y memory operand. And YAR, Y memory AR selection field defines the AR that contains the address of Y memory. So whatever we are going to use, either it is having auxiliary register followed by X memory and Y memory. So this is what we understand from a function of this opcode and xmod and ymod functions and its functions. So this is a block diagram of indirect addressing with the dual data memory operand. So this you have to just go through the diagram. So diagram is required for each and every operand addressing what we consider. Then memory mapped register addressing. It is used to modify the memory mapped register without affecting the data pointer, or what we call it as data page pointer or a stack pointer. So there is a overhead for writing to a register which is minimal. So usage of this memory map register will override this problem of writing it to a register very less, and it is working for direct and indirect addressing. So this is useful for both the direct and indirect addressing. And scratchpad RAM located on page E0 can be modified. So these are the RAM which are located on this DSP TMS320 device. Then STM store memory, and again STM store memory. So content X to direct, so this is a location, or content TB1 to AR1. So this some value or some address can be stored directly into a auxiliary register, or it is pointed directly to a memory location. So this direct is a memory location. So anything can be used. So in detail we will go with the instruction, so that would be better instead of using time more on this concept. So 16-bit memory map register address generation. So this is how the address generation is performed by the DSP device in a 16-bit memory mapped register. Then what we have is a stack addressing. So here it is used to automatically store the program counter during interrupts and subroutines. So stacks are normally used for interrupts and subroutines, and it can be used to store also the additional items of a context or to pass the data value. So for passing any data values, we require a stack, and it uses a 16-bit memory mapped register which is a stack pointer. So this is the stack pointer before operation and after operation. So x1 value is 0011. It means that in 0011 x1 we have as a variable which is pointed by a stack pointer. Similarly, if I go with the stack pointer 0010, the pointer which is pointed early to 0011 is now pointing to 0010. So x1 will be in 0011 and x2 will be in 0010. So this is the values of stack before and after operation. So if I look into the example, assuming the current content of AR3 to be 200, what will be its content after each of the following PMST 54 modes is used? Assume that the contents of AR0 are 20 H. So AR0 content is given as 20 H and AR3 current content is 200 H. So what will be the content when this instruction is executed? So AR3 plus 0 means the AR3 plus AR0. So this refers to AR0. Similarly, AR3 minus AR0, this refers to AR0. So using this instruction, we are going to find what is the result. One is 200, one is 20. So either we are adding the content of AR0 to AR3 or we are going to subtract the content of AR0 from AR3. So this is what we do under this example. And again AR3 pointing to AR3 and AR3 40H, AR3 minus 40. These are the offset addresses what we are going to consider. So AR3, so content of AR3 plus content of AR0 is stored in AR3. So the content of AR3 is 200, content of AR0 is 20. So it is 220H is stored in AR3. Similarly, the other one AR3 minus AR0, so 200 minus 20H is 1E0H. Similarly, the content of AR3 is incremented by 1 and it is being stored in AR3. So 200 is the content of AR3, so it gets stored in AR3. So 200 plus 1 is 201 and it is stored in AR3. Similarly, AR3 minus 1, 1 FFH which is stored in AR3. And in the next case, AR3 is not modified because we are just pointing to the content of AR3. So AR3 is already having a value 200H. So it is not modified. Then AR3 plus 40H. So we are going to add the content of AR3 with the 40. So that is 40 is the offset address what we had in the small bracket here. Like this 40H was given. So this has been added as an offset. So 200 plus 40 is 240H. Similarly, the other one AR3 minus 40 is 200 minus 40, 1C0H. So this is how we are going to solve this type of problem. Then assuming that the register AR3 with the contents 1020 is selected as a pointer for a circular buffer, let BK is a circular buffer size which is 40H. To specify the buffer size of 40H, so this is known, determine the start and the end address for the buffer. So what will be the contents of the register AR3 after the execution of this instruction? And the contents of AR0 are 0025H. So AR3 content is 1020H, means that it is pointed currently to 1020H. Then masking the lower 6 bits gives the starting address of the buffer. So we are going to mask the last 6 bits, that is lower 6 bits, so that they are made zeros, which gives us the starting address of the buffer. So if I mask this 6 bits of this 1020, I'll get it as 1000H. Then replacing the same bits with the BK gives the end address. So BK value is 40, so I am going to add this to 1000H. So this is going to be added and this gives us 1040H. So we can see that 1040H. Then if I go with the instruction LD AR3 plus 0, comma A modifies AR3 by adding the content of AR0 to it and applying circular modification. So what happens? It yields AR3 equal to circular addressing or modification of 1020H plus 0025H, which is given. So it is circular of 1045H. So circular of 1045H is obtained by subtracting BK. So start address is obtained by adding BK, end address was obtained by subtracting BK. So with this instruction, what I do, I'll just add the content of auxiliary register 0 with 1020, which is giving me 1045H. Then AR3 will have the circular modification of 1045H, which is obtained by subtracting the value of BK from 1045H, which is the content of AR3. So giving us 1045H. 1005H. So thus the location 1005H is pointed by AR3. Similarly, assuming the current contents of AR3 is 200, what will be the content after each of the following addressing modes is used? So assume that the contents of AR0 are 20H. So AR3 is given, AR0 is given. So AR3 is 200, AR0 is 20. So 0B, B represents a bit reversed addressing mode. So AR3 content is AR3 plus AR0 plus reverse carry propagation. So that is bit reversal. So 200 plus 20H is anyway giving us 220H without any modification, even if reverse carry propagation or bit reversal is done. Similarly, AR3 minus AR0 is 200 minus 20H, which is giving us 23FH if I go with reverse carry propagation. Then this is a function of different pin PMST register. So you can just go through this. So what is this PMST? That is one is overlay, one is DROM, one is microprocessor or microcontroller bit. So if it is 0, ROM is enabled. If it is 1, ROM is not available or disabled. If OVLY is disabled, RAM is in the data space. If OVLY is enabled, RAM is in the program space. Similarly, DROM, if it is 0, ROM is not in the data space. If it is 1, then only the ROM is in the data space. So this is how we are going to consider this session.